K2-18b, History, Present and Future. Can we live on K2-18b? Introduction. K2-18b, an intriguing exoplanet located approximately 120 light-years away in the constellation Leo, has captured the attention of astronomers and astrobiologists since its discovery in 2015. With a mass about 8.6 times that of Earth, K2-18b falls into a category of planets known as sub-Neptunes. This report explores the history of K2-18b, its current observations, and its potential for future habitability. History of K2-18b. Discovery 2015. K2-18b was first identified by NASA's K2 mission, an extension of the Hubble Space Telescope's mission dedicated to discovering exoplanets. The planet orbits a cool dwarf star K2-18 located within the habitable zone where conditions may be suitable for liquid water. Initial observations 2019. The Hubble Space Telescope provided the first atmospheric analysis detecting hints of water vapor in K2-18b's atmosphere. This finding stirred excitement regarding the planet's potential habitability. Significant findings 2023. In September 2023, the James Webb Space Telescope JWST made groundbreaking observations confirming the presence of methane and carbon dioxide in K2-18b's atmosphere. These gases, combined with the low levels of ammonia detected, bolstered the hypothesis that K2-18b could be classified as a Hycean planet characterized by a hydrogen-rich atmosphere and possibly vast oceans. Current observations and controversies. Despite the exciting potential suggested by JWST's findings, a significant debate emerged in 2024 challenging the notion that K2-18b is a candidate for habitability. A study led by Nicholas Wogan suggested that K2-18b might be a gas-rich planet lacking a solid surface, casting doubt on its classification as a Hycean world. This new interpretation posited that the atmospheric composition could be explained through different models, indicating that K2-18b may not support life as we understand it. Key discoveries from JWST. 1. Atmospheric composition. The presence of methane and carbon dioxide was confirmed, with a notable absence of ammonia. This composition hinted at a potential water ocean beneath the atmosphere. 2. Potential biosignatures. Initial findings included weak evidence for dimethyl sulfide DMS, a molecule associated with life on Earth primarily produced by marine phytoplankton. While this sparked interest, the detection remains tentative and requires further validation. 3. Contradictory models. The debate continues as contrasting models, one supporting K2-18b as a habitable ocean world and the other as a gas-dominated planet, emerge from the observations. Understanding Hycean worlds. The concept of Hycean planets introduced in recent studies suggests a new category of potentially habitable worlds that could possess dense hydrogen atmospheres and vast bodies of water. K2-18b is a prime candidate for this classification due to its size and atmospheric characteristics. Potential for life. Hycean worlds could harbor unique forms of life that differ from terrestrial organisms, expanding our understanding of habitability in the universe. Future prospects. Ongoing research. The exploration of K2-18b is far from over. Future observations with JWST and other upcoming missions aim to clarify the planet's atmospheric composition. The confirmation of DMS or other biosignatures could significantly impact our understanding of K2-18b's potential for life. Technological advancements. The JWST has demonstrated unprecedented capabilities in characterizing exoplanet atmospheres, paving the way for future missions aimed at identifying habitable conditions beyond our solar system. Conclusion. While K2-18b presents an exciting possibility for habitability, the ongoing debate among scientists highlights the complexities of studying exoplanets. Despite conflicting interpretations, the potential for discovering life in unusual environments remains a captivating endeavor in astronomy. K2-18b serves as a reminder of the vastness of the cosmos and our quest to understand our place within it. Future observations will likely provide further insights into this enigmatic world. As scientists continue to seek answers about life beyond Earth. Timeline of key events. 2015, K2-18b discovered by NASA's K2 mission. 2019, Hubble Space Telescope detects water vapor in K2-18b's atmosphere. 2023, JWST confirms methane and carbon dioxide hints at potential oceans. 2024, new study questions K2-18b's habitability, suggesting it may be a gas-rich planet. What's next? As we look to the future, K2-18b stands as a focal point in the search for extraterrestrial life. The scientific community's commitment to exploring this exoplanet may one day yield answers to the age-old question, are we alone in the universe? With each new discovery, we draw closer to understanding the diverse and complex nature of planets beyond our own. K2-18b, an intriguing exoplanet located approximately 120 light-years away in the constellation Leo, has generated significant interest among astronomers since its discovery in 2015 through NASA's K2 mission. The planet boasts a mass about 8.6 times that of Earth, placing it in a category of exoplanets known as sub-Neptunes. These planets are characterized by their size, which lies between that of Earth and larger gas giants like Neptune. The unique properties of K2-18b, especially regarding its potential to harbor life, have been a focal point of recent studies. In September 2023, the James Webb Space Telescope JWST made a groundbreaking discovery revealing the presence of methane and carbon dioxide in K2-18b's atmosphere. This finding led to discussions about the possibility of K2-18b being classified as a Hycean planet, which is theorized to have a hydrogen-rich atmosphere and a surface covered with oceans. This categorization is intriguing because it suggests that such planets could possess conditions conducive to life, expanding the types of environments in which we might search for extraterrestrial organisms. However, the narrative surrounding K2-18b's habitability is not straightforward. A study published in March 2024 challenged the Hycean hypothesis, proposing instead that K2-18b might be a gas-rich planet lacking a solid surface capable of supporting life. The research team led by Nicholas Wogan utilized models to analyze the data from JWST, indicating that K2-18b may not possess the essential components such as sufficient ammonia and water vapor typically associated with habitable environments. This renewed skepticism highlights the complexity and variability in interpreting atmospheric data from exoplanets and the ongoing debate regarding K2-18b's true nature. The initial findings from JWST had suggested that the abundance of methane and carbon dioxide combined with a low concentration of ammonia could indicate the presence of liquid water beneath a hydrogen-rich atmosphere. The potential detection of dimethyl sulfide (DMS), a compound largely produced by marine phytoplankton on Earth, further fueled speculation about the possibility of life on K2-18b. Nevertheless, the lack of strong evidence for ammonia raised doubts about the existence of a habitable ocean world. The contrasting views on K2-18b's habitability underscore a counterintuitive aspect of exoplanet research. The same atmospheric data can lead to vastly different interpretations regarding a planet's ability to support life. While some researchers emphasize the potential for life in environments previously considered inhospitable, others caution against drawing premature conclusions without more robust evidence. Furthermore, the exploration of K2-18b raises important questions about the nature of life and the conditions that might support it. Traditional searches for life have predominantly focused on rocky Earth-like planets. But the notion of Hycean worlds introduces the possibility that life could exist in vastly different environments than our own. The findings from K2-18b challenge our understanding of habitability and encourage a broader perspective on the types of planets that may be capable of supporting life. As research continues, future JWST observations are anticipated to provide more insights into K2-18b's atmospheric composition and its potential for habitability. These upcoming studies will be crucial in validating the presence of DMS and characterizing the abundance of other atmospheric constituents. The ongoing investigation into K2-18b exemplifies the dynamic and evolving nature of exoplanet research, where new discoveries can rapidly reshape our understanding of the universe and our place within it. The case of K2-18b serves as a reminder of the complexity inherent in exoplanetary science, where counterintuitive findings can arise from the same dataset, reflecting the need for continued exploration and analysis in the search for life beyond Earth. The ongoing study of K2-18b not only has the potential to uncover new knowledge about this specific exoplanet, but also to expand our understanding of the diverse conditions that could support life in the cosmos. As we look to the future, the exploration of K2-18b and similar exoplanets may yield valuable insights that challenge our preconceived notions about habitability and life beyond our solar system. K2-18b is an exoplanet located in the constellation Leo, approximately 120 light-years from Earth. With a mass about 8.6 times that of Earth, K2-18b has garnered significant attention since its discovery by NASA's K2 mission in 2015, particularly concerning its potential habitability. The recent observations made by the James Webb Space Telescope JWST in September 2023 revealed the presence of methane and carbon dioxide in K2-18b's atmosphere, igniting discussions about its classification as a Hycean planet, which implies it might possess a hydrogen-rich atmosphere and surface oceans. Important findings often overlooked. 1. Ambiguity in atmosphere composition. While the discovery of methane and carbon dioxide is exciting, the low levels of ammonia and the absence of water vapor in significant amounts raise questions about the planet's habitability. The implication that K2-18b might not have a substantial water ocean challenges the initial Hycean hypothesis. This nuance is crucial because it suggests that while K2-18b could have conditions favorable for life, its atmosphere might not support the existence of life as we know it. 2. Rival hypotheses. The debate around K2-18b's classification as a Hycean world versus a gas-rich planet is significant. A study published in March 2024 posited that K2-18b could be a gas giant lacking a habitable surface, which contradicts previous assumptions. This highlights the importance of considering alternative interpretations of the data rather than quickly jumping to conclusions about potential life. The ongoing dialogue surrounding K2-18b underscores the dynamic nature of exoplanet research and the need for ongoing observations to refine our understanding. 3. Dimethyl sulfide DMS detection. The potential detection of dimethyl sulfide DMS is remarkable, as on Earth this compound is primarily produced by marine phytoplankton. This finding could suggest biological processes at work. However, the detection is still tentative and requires further validation. The excitement surrounding DMS often overshadows the fact that its presence alone does not confirm life. Alternative non-biological processes could also yield similar signatures. This nuance is often overlooked in discussions about biosignatures. 4. The role of stellar characteristics. K2-18b orbits a cooler dwarf star, which affects its environmental conditions. The star's lower temperature and potential for flaring could create a hostile environment for life. Many discussions around K2-18b focus solely on the planet itself, neglecting how its stellar environment might influence its habitability. Understanding these interactions is crucial for assessing the potential for life on K2-18b. 5. The challenge of atmospheric models. The atmospheric models used to interpret the data from K2-18b are complex and often debated. While models indicate that K2-18b could support a hydrogen-rich atmosphere and possibly liquid water, the actual conditions may differ significantly due to the planet's unique characteristics. The scientific community should remain cautious about making definitive claims based solely on model outputs without extensive observational validation. 6. Lack of direct measurement. Current data on K2-18b are based on indirect observations primarily through transmission spectroscopy, which relies on light from the host star passing through the planet's atmosphere. This technique has limitations, as it may not capture the full picture of the atmospheric composition. The potential for cloud cover and other atmospheric phenomena could obscure significant features, leading to incomplete or misleading conclusions. Significance of these findings. Broader implications for exoplanet research. K2-18b serves as a case study for the broader challenges faced in exoplanet research. The debates surrounding its habitability reflect the intricacies involved in studying distant worlds. The findings emphasize the need for ongoing research and the importance of multiple observational campaigns to build a comprehensive understanding of exoplanet atmospheres. Revisiting habitable zone concepts, the discussions about K2-18b challenge traditional notions of what constitutes a habitable zone. The idea that larger gaseous planets could harbor life-supporting conditions expands the scope of astrobiology and encourages researchers to explore unconventional environments in the search for extraterrestrial life. Cautious optimism. While the findings are tantalizing, they also serve as a reminder of the complexity of life's requirements. The excitement around K2-18b must be tempered with a cautious approach, recognizing that the presence of certain gases does not guarantee the existence of life. This balance is essential as the scientific community navigates the challenges of interpreting exoplanet data. In conclusion, while K2-18b is a compelling target in the search for extraterrestrial life, a careful examination of its atmospheric characteristics, stellar environment, and the implications of its findings is critical. The ongoing research and future observations will undoubtedly continue to refine our understanding of this intriguing exoplanet and its potential for supporting life. The exploration of K2-18b has captured the attention of scientists and astronomers due to its unique characteristics and potential for habitability. This analysis identifies four pivotal points in the discussion surrounding K2-18b, emphasizing its atmospheric composition, the controversy over its classification as a Hycean planet, the implications of potential biomarkers, and the future of exoplanet studies. 1. Atmospheric composition. The discovery of methane and carbon dioxide in K2-18b's atmosphere by the James Webb Space Telescope JWST is significant. These molecules are essential for understanding the planet's potential for habitability. The presence of methane in particular raises questions about possible biological processes, as it is often associated with life on Earth. The findings also indicate a low abundance of ammonia, which is surprising given expectations for a planet of K2-18b's type. The atmospheric composition suggests that K2-18b may harbor a hydrogen-rich atmosphere, potentially with liquid water beneath, aligning with the characteristics of Hycean planets. However, atmospheric analysis is complex, and these findings do not definitively indicate that K2-18b is habitable or inhabited. The presence of methane does not confirm life; it could also originate from geological processes. The atmosphere's thick nature complicates the study, as it can obscure other molecules, making it difficult to ascertain the true nature of K2-18b's environment. 2. Controversy over Hycean classification. The classification of K2-18b as a potential Hycean planet, a type of exoplanet with a thick hydrogen atmosphere and possible oceanic surface, has sparked debate. While some researchers argue that the presence of methane and carbon dioxide supports this classification, others suggest that K2-18b might be a gas-rich planet lacking a habitable surface. This contention arises from differing interpretations of the same data, leading to a significant academic discussion about the criteria for classifying exoplanets and determining their habitability. The contrasting models highlight the challenges in exoplanet studies, particularly regarding the interpretation of atmospheric data. The debate emphasizes the need for further observations and research to clarify K2-18b's true nature and assess its potential for supporting life. 3. Implications of potential biomarkers. The potential detection of dimethyl sulfide DMS in K2-18b's atmosphere presents exciting implications for the search for extraterrestrial life. On Earth, DMS is primarily produced by marine phytoplankton, leading to speculation about the possibility of biological processes on K2-18b. This finding, however, tentative fuels interest in the planet as a candidate for further study in the quest to discover life beyond Earth. The presence of such biomarkers is crucial for understanding the potential for life on exoplanets. It opens discussions on what constitutes life as we don't know it, encouraging scientists to expand their definitions and frameworks for habitability. The exploration of these biomarkers requires rigorous verification, and future observations with JWST will be critical in confirming or refuting these initial findings. 4. Future of exoplanet studies. K2-18b represents an exciting opportunity for future exoplanet research. As the most detailed atmospheric analysis of a habitable zone sub-Neptune to date, it highlights the capabilities of JWST in advancing our understanding of exoplanets. The ongoing debate about K2-18b's classification underscores the importance of continued observations and the development of new models to interpret complex data. Future missions and studies will likely focus on confirming the presence of biomarkers, exploring the planet's atmospheric dynamics, and further characterizing its environment. The findings from K2-18b may also inform the search for other potentially habitable worlds, expanding our knowledge of the types of planets that could support life in the universe. As technology advances, the scope of exoplanet studies will continue to grow, revealing a more nuanced understanding of planetary atmospheres and the conditions for life beyond our solar system. In conclusion, K2-18b serves as a compelling case study in the search for extraterrestrial life, emphasizing the complexities of atmospheric analysis, the ongoing debates regarding planetary classification, the significance of potential biomarkers, and the future directions of exoplanet research. Each of these points contributes to a broader understanding of our universe and the potential for discovering life beyond Earth. 1. The case of Mars habitability. The exploration of Mars has been a significant historical case in the search for extraterrestrial life. The Mars missions, including the Viking landers in the 1970s and more recent rovers like Curiosity and Perseverance, aimed to uncover signs of past or present life on the planet. Early Viking experiments suggested microbial life might exist, but later findings indicated the absence of organic molecules. The ongoing debate over the planet's potential for habitability aligns closely with the discussions surrounding K2-18b, as both involve the search for life in environments previously thought inhospitable. 2. The Goldilocks zone debate. The concept of the Goldilocks zone or habitable zone emerged from the study of exoplanets and their potential to support life. This debate began gaining traction in the early 1990s with the discovery of exoplanets. Just as K2-18b's position within its star's habitable zone is scrutinized for potential life, many historical cases have examined planets like Earth, Venus, and Mars in relation to their distances from the Sun and their ability to support liquid water. The ongoing examination of planets within their Goldilocks zones continues to be a focal point in astrobiology. 3. The Voyager missions and the search for extraterrestrial life, launched in 1977. The Voyager missions provided humanity's first detailed images of the outer planets and their moons. The discoveries made by the Voyager spacecraft, especially regarding the atmospheres of Jupiter's moon Europa and Saturn's moon Enceladus, suggested the potential for subsurface oceans, raising questions about their habitability. This historical case parallels the investigation of K2-18b, as both involved the search for environments that might support life beyond Earth. The legacy of the Voyager missions continues to influence our understanding of where and how life might exist in the universe. Future outlook on K2-18b. Can we live there? K2-18b, an exoplanet about 120 light-years away in the constellation Leo, has captured the attention of astronomers and astrobiologists since its discovery in 2015. With a mass approximately 8.6 times that of Earth, K2-18b lies in the habitable zone of its host star. K2-18. Recent observations from the James Webb Space Telescope JWST have revealed intriguing details about its atmospheric composition, including the presence of methane and carbon dioxide, potentially hinting at the existence of liquid water beneath a hydrogen-rich atmosphere. Predictions for the future. 1. Enhanced understanding of exoplanet atmospheres. Future observations with JWST and other next-generation telescopes are expected to provide deeper insights into the atmospheric conditions on K2-18b. As more data becomes available, scientists will refine their models and hypotheses regarding the planet's atmosphere, potentially confirming or challenging the Hycean planet classification. The anticipated data may also help determine the presence of ammonia, which could further clarify the planet's habitability. 2. Potential for life. The possibility of life on K2-18b remains a topic of debate. While the detection of dimethyl sulfide DMS, a compound associated with biological processes on Earth, has sparked excitement, it is not definitive proof of life. Future studies could either bolster the argument for habitability or suggest alternative abiotic processes that might explain the atmospheric composition. As our understanding of extremophiles on Earth expands, so too may our definitions of what constitutes a habitable environment. 3. Technological advancements in exoplanet research. As telescope technology continues to advance, the ability to analyze exoplanet atmospheres will improve. The JWST, along with other planned missions like the European Space Agency's Ariel, will allow for more sensitive measurements, potentially leading to the discovery of additional biosignatures or other chemical markers indicative of habitability. These advancements could lead to a more comprehensive understanding of K2-18b and its potential to support life. 4. Interdisciplinary collaboration. The study of K2-18b will likely inspire collaborations across disciplines, integrating insights from astronomy, chemistry, geology, and biology. This interdisciplinary approach may foster new methods for detecting life and understanding planetary processes, potentially leading to the development of innovative technologies and models for studying exoplanets. Can we live on K2-18b? The question of whether humans could live on K2-18b hinges on several factors. 1. Atmospheric conditions. If future studies confirm that K2-18b has a dense hydrogen-rich atmosphere with significant water presence, it may not be directly hospitable to human life as we know it. The atmospheric pressure, temperature, and chemical composition would need to be compatible with human survival. 2. Environmental challenges. The atmospheric and surface conditions of K2-18b, whether it is a water world or a gas giant, pose significant challenges. High pressures, extreme temperatures, and a lack of solid ground would complicate any attempts at colonization. Additionally, potential high levels of methane could present further risks. 3. Technological solutions. Should K2-18b be deemed a candidate for future exploration, advancements in technology could one day allow for human adaptation to its environment. Concepts such as bioengineering, terraforming, or the construction of protective habitats could be explored as ways to facilitate human life on other planets. For ethical considerations, the pursuit of living on K2-18b would also require ethical considerations regarding planetary protection and the potential impact on any existing ecosystems should they be found. This aligns with the broader questions of our responsibility as explorers and the implications of altering alien environments. Conclusion. While K2-18b presents a tantalizing possibility for life beyond Earth, its actual habitability remains uncertain. Future research will play a critical role in determining whether this exoplanet could support human life or harbor life forms of its own. The continued study of K2-18b will not only expand our understanding of planetary systems but will also serve as a stepping stone for humanity's journey into the cosmos, shaping our quest to find a second home among the stars.